When I first started teaching about transmission lines, I first went through all the transmission line theory, starting with the telegrapher equations and finding solutions and impedances and discussing waves and reflection coefficients and such, and a great mathematical structure to describe the behavior. And then at the end, I talked about physically, how do we build transmission lines? What is a transmission line? How do we know one when we see it? But I found that students during the mathematical explanation of transmission lines were a bit impatient if they didn't really understand what it was that I was describing to them. Some students, I think, were even uncertain whether transmission lines were, in fact, physically real, or were they just simply a mathematical abstraction that I was describing. So I've learned to go ahead and, before I talk about the mathematical explanation of transmission line theory, to talk a little bit about the physical structure, so you know what it is that we're going to be describing. Now, this has its own set of problems and issues, in that it's hard to describe them physically without first talking about the parameters of a transmission line. So I'm going to talk about some of the common transmission lines that we use in electrical engineering. I'll talk about some of their physical parameters. You may not understand all of those until we get further later in the course and really do a full mathematical explanation. So the first transmission line that I'm going to talk about, physical transmission line, is the coaxial transmission line. And I start with this one for a number of reasons. One, it is probably the most prevalent of all transmission lines. It is also the most sort of mathematically pure. It is a true transmission line. We'll talk about what that means here in a second. Now, I brought a visual. Most of you probably have seen a transmission line, a coaxial transmission line of this type. Now, connectors like this, what we call the F connector, that was used in the old VCRs and TVs, are certainly not as prevalent as what they once were, but they're still around. You know, these things are a coaxial transmission line for transmitting high frequency essentially television signals for quite some time. So what is a coaxial transmission line? It essentially is two circular cylinders, one inside the other. Two conductors. Remember, we talk about transmission lines always having two conductors and two wires. And in this case, one conductor is what we call the inner conductor. This is a circular cylinder of conducting material. And then it is inside a second conducting cylinder, which we call the outer conductor. That should actually say outer conductor, not inner conductor there. Separating these two conducting cylinders is, generally speaking, some sort of material that is non-conducting, that is an insulator, that is a dielectric. And that is the simple structure, then, of a coaxial transmission line. So the length of the transmission line runs this way. If we were to go through and slice it in half, this would be the cross-section that we would see. So this red cylinder is the inner conductor. It's a conducting material. The key parameter of the inner conductor is its outer radius A. The outer conducting conductor, its key parameter, physical parameter, is simply the distance from the center to the inside of the outer conductor. So we call this the inner radius of the outer conductor, and it is defined by the value B. The material that separates them, gives its physical strength, is the dielectric, plastic of some type, perhaps, that has some dielectric constant. Now, electromagnetically, what's happening inside this coaxial transmission line? This gives an image of essentially the fields that are inside. What we're going to find is that there is an electromagnetic wave propagating, actually two of them, propagating along this coaxial line, like there is for all transmission lines. And yes, I said electromagnetic waves, electric fields and magnetic fields associated with them. Now, this should be no surprise, because if we have current, we are going to have magnetic fields or magnetic flux densities. If we have voltage, then we're going to have electric fields. That's true of all circuits. Voltages result from electric fields, and currents result from magnetic fields, or vice versa, depending on your viewpoint of how it works. Of course, they're coupled together. So if we were to look at the fields inside of a coaxial transmission line, this is a cross section, just basically replacing this with the fields inside, we would find the electric field extends from the center outward toward the outer conductor. If we look at the mathematics of the coaxial transmission line, since it's two cylinders, we typically use cylindrical coordinates. We place the center of the cylinders, both cylinders, along the z-axis. And so as we move away from the center, we move away from the z-axis, we're moving in the direction of increasing rho, our cylindrical coordinate rho being the distance from the origin. And if the direction of increasing rho then is always pointing away from the z-axis. And that direction we can call a sub rho. That's the unit vector that describes that direction, that is always pointing away from the z-axis. Wherever you are, you locate the z-axis, and if you turn around and point the other direction, that is the unit vector a sub rho. That unit vector describes the direction of the electric field. The electric field at every point in the coax is going to be pointed in a direction away from the z-axis, from the center of that coaxial transmission line. What about the B field, the magnetic field? Well, current's going to flow along the conductor, either down down and back, since we're AC signals happen here. The current oscillates back and forth, and the resulting magnetic flux density or magnetic field is a solenoidal field that circles around then the inner conductor. And so the direction of that field is the direction of increasing phi, phi being the coordinate of the cylindrical coordinate system, and that describes then the direction of the magnetic field, a sub phi. The third direction, of course, the third unit vector of the cylindrical coordinate system is a sub z, and that describes the direction of increasing z, so that points down the line. Notice that the electric field, the magnetic field, has no component in the direction of z, a sub z, this unit vector. It turns out the wave itself that is created, this electromagnetic wave consisting of electric field and magnetic field, actually propagates in the direction of a sub z. It'll propagate down the line in one direction or the other direction, or as we'll find later, generally both simultaneously. The direction of power flow, then an electromagnetic wave carries energy along with it, and so the energy is carried in the direction of a sub z. And so we have an electromagnetic field that we call a TEM wave. We find that the wave that is propagating, electromagnetic wave, has an electric field and a magnetic field that are transverse, in other words, orthogonal to the direction of propagation. And of course, a sub rho, a sub phi, and a sub z are three unit vectors that form a orthonormal set for the for the cylindrical coordinate system. So this TEM wave is a requirement of a true transmission line. A transmission line has two conductors, and it creates a TEM electromagnetic wave propagating along that transmission line. And again, the only thing to really remember there is that the electric field is orthogonal to the direction of propagation, the magnetic field is orthogonal to the direction of propagation, and then the electric and magnetic field are orthogonal to each other. Now we have those two conductors, and in most cases, certainly we build those conductors a very good conducting material. So the resistance of each is very small, so small we can essentially discard it or consider it to be zero. Likewise, the dielectric between the two conductors of our coaxial line, we assume to have a conductivity that's very low, so low that we can consider it to be zero, and therefore have essentially a perfect insulator between the two. The other parameters, though, of wires, as we talked about earlier, are the capacitance per unit length and inductance per unit length. And these, of course, we cannot discard if the signals, if the currents and voltages that we are using are of high frequency. And this really, again, sort of requires us to distinguish what we call a transmission line from simply a couple of wires. And if we have high enough frequency that the induced voltages due to the inductance are significant and cannot be ignored, and the displacement current from the capacitance are significant and cannot be ignored. So we need to figure out what is the capacitance and inductance per unit length of these wires. If you go back to your elementary electromagnetics text, excuse me, in course, you probably went through and determined these two values using electrostatic principles. And of course, this is the interesting thing. We weren't talking about any time varying signals, just simply an omega equal to 0, a static electric field. We could go through and find that the capacitance per unit length of a coaxial line was equal to this. And notice these parameters are the parameters of the coaxial transmission line, B over A, B being the outer radius of the inner conductor, the inner radius of the outer conductor rather, and A being the outer radius of the inner conductor. And then of course epsilon is the dielectric that separates those two. So with these parameters, BA and epsilon, we can determine then the capacitance per unit length of a transmission line. Electrostatic analysis that gives us the correct capacitance. Likewise, we can use magnetostatics to go through and find the inductance per unit length for this transmission line. Once again, it depends on the two radius, B over A. Notice it does not depend on the dielectric. So we can use these then to understand how our transmission line works. Again, that's the real issue with transmission lines. There are wires where the capacitance and inductance per unit length cannot be ignored. They have to be accounted for in the mathematics. We'll find later in our analysis of transmission lines and its mathematical behavior that we sort of transform these two parameters L and C into two other real parameters that have more direct physical meaning to us with respect to electromagnetic wave propagation. The first of these is what we call characteristic impedance of a transmission line. And the characteristic impedance of a true transmission line is simply the square root of the ratio of inductance per unit length to capacitance per unit length. That's true for all true transmission lines. And of course, for a coax, since we know the inductance and capacitance per unit length, we can insert the previous expressions to come up with a relatively simple expression for the characteristic impedance of a coaxial transmission line. Notice again, it depends on the three parameters, epsilon, B, and A, the two radius there. Likewise, we take L and C and we can convert that into a more fundamental parameter in wave propagation that we call beta. Beta is the square root of the product of L and C times the value of omega. So it's kind of an interesting symmetry here. Here we take the ratio of L and C and take the square root. Here we take the product of L and C and take the square root and of course multiply by omega. So these two parameters, characteristic impedance Z0 and beta, are going to be fundamental parameters. We're really not going to talk about inductance per unit length and capacitance per unit length in transmission line behavior once we do the transformation to Z0 and beta. Again, what are these values? Don't worry right now. We'll get to that when we start talking about transmission lines. The key thing here, the takeaway, is that these values, these fundamental parameters of electromagnetic wave propagation and transmission line depend, in this case, very simply on the structure of that transmission line. Later we'll show as well that the velocity of a wave propagating in a transmission line is simply equal to omega, its radial frequency, 2 pi times f, the cycles per second of the oscillation, divided by this value of beta. And we'll show that there's interesting symmetry associated with this in terms of the units of omega and beta. If we insert the previous results from the previous page in there, we can find that velocity is going to be equal to this. And notice C here is the speed of light. It's the speed of light divided by 1 over the square root of the dielectric constant inside of that coaxial transmission line. And of course, if this relative dielectric constant were equal to 1, then the velocity of electromagnetic propagation would be c, the speed of light. And of course, that's because c is the speed of electromagnetic propagation in free space. So one question is, how big should these coaxial cables be? If you look at the cable that I had at the beginning of this lecture, its outer diameter is probably a little bit less than a centimeter. So why is that? How do we determine what the values of B and A should be? Well, of course, the values of the radius, both outer and inner, will affect many things. One is simply the size of that coax, and the bigger the coax, it's going to be heavier, and of course, it's going to be more costly, particularly for the conductors that we use for the inner conductor and the outer conductor. So you might make an argument that we should make this as small as possible. If we make it small, we can make it lightweight. We can put more coaxials together in a same volume or same cross-sectional area there, and of course it would cost us less money. But we'll find that we also want to make sure that our transmission lines have good power handling capabilities, that we have to concern ourselves with the rate of energy flow down that transmission line. From that standpoint, we find that we want to make the size of our transmission lines bigger. And so there's a bit of a conflict there. So for example, for a given line voltage, let's say between the two conductors, we find that reducing the radiuses, reducing the distances between these two conductors, cause the electric field inside between these two conductors to increase. Why is that? Well, electric field, remember, is volts per meter. And so for a given voltage, as we reduce the distance between them, we reduce the distance in meters, the electric field in volts per meters will increase. The electric field will get more intense inside of this coaxial line. So what problems might that cause? The first problem is that we might have greater line attenuation, that the propagating wave will lose some of its energy as it propagates. Now, I know we said that the dielectric between the two conductors we assume to be a perfect insulator, and therefore the conductivity we model is essentially equal to zero. And this is a very good approximation as long as our transmission line, coaxial transmission line, isn't particularly long, let's say a meter or so. As we go longer, however, even though the dielectric losses will be small, they'll start to add up a little bit. And so the approximation, of course, that we use of zero isn't going to be quite right, and we'll start to see some loss. How much loss will depend on the value of the electric field. As the electric field gets more intense, then it will convert more energy into heat as it propagates along. As we make the dielectric space, the space between them, larger, then we will get less loss, generally speaking, of that propagating wave. The second problem that we have is one of dielectric breakdown. And this is just one as we try to put too much power down our transmission line, propagating down our coaxial transmission line. Of course, the voltage between the two conductors will increase, and because of that, the electric field between the two conductors will increase. As we increase the electric field, of course, the dielectric, the dipoles within the dielectric will begin to stretch. They'll begin to polarize, and they can only stretch so far. It's like stretching a rubber band. The dipoles in from the material in the dielectric, at some point they stretch and then they break. And we're very familiar with this phenomenon. It's exactly what happens in lightning. Large electric field between the ground and the atmosphere builds up. The atmosphere, the constituent gases of the atmosphere begin to stretch as they polarize. At some point they stretch so much that finally they shred, they ionize, and that's when we get a lightning strike. Similar thing happens if you shuffle your feet along the carpet and reach over to touch, let's say, a metal doorknob. As you get closer and closer to the doorknob, the electric field gets larger and larger, more and more intense. As the distance between you and the doorknob gets smaller, the electric field gets intense, the air between you and the doorknob will begin to polarize more, and at one point, finally, that air will ionize, and you'll have a tiny little lightning strike that happens between your finger and the doorknob, and of course it gives you a bit of a shock. Same thing can happen in our coaxial transmission line. As the power of the electromagnetic wave gets larger, again, the electric field gets bigger. At some point, we'll have dielectric breakdown. The dielectric will essentially ionize, and we'll get current that flows from the outer conductor then to the inner conductor. The assumption of conductivity being very low will go out the window and become very high, and oftentimes we can just literally blow a hole into our coaxial cable. So that says something to do with the size of the coaxial cables that we use. How much power is going to be, or energy, what rate at which energy is going to be flowing through that transmission line will determine how big our transmission line needs to be. Again, generally speaking, we'd like to make it as small as possible, but it needs to be able to handle the power we're going through it. Now, one last statement. We're not going to talk much about it here, but there is an upper limit on how big you make it as well. If you make your coaxial line too big, you will make it so large that you can start to propagate waveguide modes, higher order modes. Your TEM solution, our assumption for the electromagnetic wave, will no longer be valid, and that will cause all kinds of issues with your electromagnetic wave propagation. So there is a lower limit with respect to the power handling capabilities. There is an upper limit associated with the waveguide mode and generating waveguide modes. But that usually, we don't have to worry about that until we get into, let's say, the tens of gigahertz before that really becomes a consideration for most coaxial lines. So having said all that, this is the reason that when we look at coaxial lines, you'll see coaxial lines with many different diameters. Again, if you have a low power situation and you don't worry for over a short distance, you don't need to worry about the loss very much. Typically, you use a coaxial line with a narrower diameter because, again, it'll save weight and cost and such. If you now all of a sudden need to propagate energy down your coaxial line from one point to the other at a very high rate, a very high power, you're probably going to need a much larger coaxial line, particularly if you're going over long distances to minimize the loss that might be incurred.